Okay, we've been discussing deadlocks for quite a while now. We looked at deadlock prevention, detection, and recovery. So, the final topic with respect to deadlocks, which we'll be looking at in the next few segments, is deadlock avoidance. So, typically, once you know what a deadlock is, when you're trying to deal with a deadlock, the sequence you will go in is you try to prevent. If you can't, you try to avoid. If that is also not possible, you have no choice but to let the deadlock happen. But once it happens, you want to detect it as early as possible, and as soon as you've detected it, you want to try to recover from it. So the typical order in which we go about trying to handle a deadlock is prevention, avoidance, detection, followed by recovery. We've been looking at those topics in quite a different sequence, but generally when we work on it in a computer, in an operating system, that is the order in which we go about things. So today we'll be looking at the last of the four, which is deadlock avoidance. So we looked at prevention, right? So when we were talking about deadlock prevention, what we did was we took those four necessary conditions. We inferred that if you break even one of these conditions, a deadlock will not happen. So we tried to see what can be done to break each condition, how feasible that is, what is the cost to be paid, and so on and so forth. Now we saw in every case that if this is done, this condition will be broken, but this is not always possible for this reason. So we had those kind of ideas which we've discussed in that segment. Now if prevention is not possible for reasons such as those enlisted in that segment, then your next best bet is to avoid a deadlock. And for avoiding a deadlock, note that avoidance does not guarantee that a deadlock will not occur at all, but to the maximum possible extent, it tries to make sure a deadlock does not happen. So for avoidance, in order to implement a sensible and working avoidance algorithm, you need some additional information, such as you might need to know that thread P will first request R1 and then R2 before releasing both resources, whereas thread Q will request R2 and then R1, and things like that. Basically, you might want to not only know which resources each process is going to ask for, but also how many instances of each and in what sequence. So you might need this type of additional information in order to be able to implement a foolproof avoidance algorithm. Now such information might not always be easy or possible to obtain, which is why sometimes avoidance mechanisms do not work. So in that case, you have to fall back on detection and recovery. But in any case, sometimes it is possible to come up with an avoidance algorithm provided you have some information like this. So of course there are multiple algorithms which have multiple requirements. So some algorithms require that you know how many instances of a resource is a process going to ask for. Some algorithms need to know the exact order in which it is going to ask for resources, all of that. We are going to look at the simplest deadlock avoidance algorithm, which only asks that you know beforehand the maximum number of resources of each type that a process may need. It doesn't want to know the sequence in which a process will claim for resources. It is P0 going to ask for monitor followed by printer followed by CPU, or monitor CPU monitor printer CPU. It doesn't want the sequence. All it wants to know is what is the maximum number of monitors, maximum number of printers, maximum number of processes each thread or each process is going to ask for. So if you have that information, we can implement this algorithm, which we'll be looking at very shortly. It's called the banker's algorithm. So before we get into that algorithm, there's a bit of terminology which we need to be familiar with. So we'll look at that. First is safe sequence. So if you are familiar with deadlock detection, which we talked about yesterday, you will be familiar with the term safe sequence. So in the detection algorithm which I explained, in the end I introduced this term called safe sequence. So I said it is the sequence in which you execute processes, you allocate resources such that they all proceed smoothly without any deadlocks or any clash for resources. So if you remember the example that we did in that segment, we allocated resources, we let a process do its job, and then we took back the resources. and we did that according to specific conditions. There was an algorithm which I will leave you to revisit that segment if you want to familiarize yourself with. But the idea was, ultimately, if I remember right, the sequence in which we executed was T0, T2, T3, T4, T1. And I said, in this sequence, if you allocate resources and execute processes, they'll run smoothly without any deadlock or any clash. Such a sequence or such an order is called a safe sequence. So again, a sequence in which processes, if executed, will proceed smoothly without any deadlock or any clash for resources is called a safe sequence. This is something we are familiar with from that previous segment. Now, if a safe sequence exists, we say the system is basically the set of processes. We say it is in a safe state, otherwise it is in an unsafe state, right? So the example we looked at yesterday, the T0, T2, T3, T4, T1, that example, you had that sequence in which you could execute without any deadlock or any sort of problem arising. So that you had a safe sequence, meaning that system is in a safe state. Now note that multiple safe sequences may exist. So we did 0, 2, 3, 4, 1. There could be another 0, 3, 4, 1, 2 or something. If you have at least one safe sequence, which is one order in which you can execute the processes without any problem, it means it is in a safe state. If no such sequence exists, we say it is in an unsafe state. Now the thing to note is, if it is in a safe state, it implies there is no deadlock, because you can execute according to the safe sequence without any problem arising. Now if it is in an unsafe state, that does not definitely mean it is a deadlock. It means there may or may not be the deadlock. So if you look at this figure, safe state, there's no problem. Unsafe state, a subset of that is deadlock. So there are a number of systems which are in an unsafe state because you cannot find a safe sequence, but not all of them will lead to a deadlock. So it is like, if you remember in your RAG, we said if there is only one instance of every resource type, then a cycle implies deadlock. But if there are multiple instances and there is a cycle, there may or may not be a deadlock, right? That kind of thing is what is happening here. You have a safe sequence, it means no deadlock. You do not have a safe sequence, it is an unsafe state, but that may or may not be a deadlock. So this is just some prerequisite terminology: safe sequence, safe state and unsafe state. So with that out of the way, we will now be moving to a couple of algorithms for deadlock avoidance.